Okay, everyone, my name is Craig, and I'm going to be your host for today's STK webinar on Apollo 11 Recreated. Today's webinar is going to be delivered by Austin Claybrook. He's to my left, which is only beneficial if you're watching this on YouTube. And he's an AGI Systems Engineer, and then we also have Cody Short. He's also on my left, and he is an Astrodynamics Software Engineer at AGI. Okay, without further ado, I'm going to send everything over to Austin, and he can get started.
Okay, well, thanks, Craig, and thank you, everyone, for attending. This has been a big project of mine. Just to give everyone just a little bit of background, I went to undergrad at Georgia Tech, and during my time down there, I worked on the Apollo missions, unrelated to this, but what I did down there was look at the extravehicular activities along with a few other co-authors of mine in a paper that got published. And what we did is we looked at the how the planned spacewalks compared to the actual spacewalks and kind of the trends on if they fell behind, what they accomplished, things like that. So during that time frame, I got intimately familiar with this document called the Apollo Mission Report, which is when the original mission reports. These got posted a couple months after the actual missions. These got posted a couple months after the missions flew. So this one, the Apollo 11 mission report, happened in 1969 in November. That's when this guy got published. And during that time, there's a whole bunch of typewritten data. This is pretty much a recap of how the mission went. With all the data in here, and that is what I used to reconstruct the Apollo 11 trajectory. So one of the motivations for doing this project was really to see the entire trajectory from start to finish. I hadn't been really able to find a complete analysis out there, and what we wanted to do is rebuild the entire Apollo mission in today's modern software using our software, predominantly Astrogator, which is inside STK, which can be used and has been used for many real missions that have been flown. Tens of missions have flown this in operations, probably hundreds used for planning. So we wanted to recreate this historic Apollo 11 event and do that inside of STK. Okay, so predominantly when we're building this, I used the Apollo 11 mission report. So let's go ahead and get started. So 50 years ago today, actually 50 years ago from yesterday, the crawler rolled out with the launch pad of the Saturn V rocket. It came out of the NASA facility down at Cape Canaveral in the Kennedy Launch Space System. Kennedy Space System or Center, and the crawler rolled out. You can see the launch vehicle roll out here, the Saturn V. There we go. The imagery is having a little bit of trouble with the GoToWebinar at the same time, but you can see the Saturn V rocket roll out. I'm just going to speed this up so we're not here all day. So right now, 50 years ago, this whole process, and you can actually see the moon in the background flying up. This whole process took a day or two to actually get the Saturn V rocket onto the pad. I remember as a kid, I was down at KSC and got to see the strip where they rolled down, and then a family friend of mine told me that these guys were going half a mile an hour, and I just couldn't believe how long it took to actually just roll this thing out. So it took a day or so to get them to the launch pad. So I'm going to speed up here just a little bit.
You may see some choppiness when things are animating on Austin's screen on the GoToWebinar, and that is unfortunately due to limitations in GoToWebinar. If you follow along on our virtual trainings that we have starting on June 4th, you'll be able to build this on your own, and you'll see that it is smooth and beautiful.
Thanks, Craig.
You don't want to do this in real time?
No, I would not like to build the mission.
Exact recreation.
Exact recreation. Well, I'm doing the best I can from the data I've had, and I'll talk about a little bit about some of the challenges of rebuilding this in a few moments. But without waiting too much longer, let's go ahead and jump to the launch. So we're jumping to the launch, and that would be on July 16th at around 9 a.m. Eastern time, about 13:32 UTCG, or like Prime Meridian time. So let me jump up actually just a few seconds before the launch so we can watch this guy. So while the launch is animating, what I'm going to do is bring up the properties of how I modeled the launch and kind of walk you through some of those details. So this is the Astrogator panel. This is what I used to rebuild the trajectory. And so as this guy's animating, I'm going to kind of articulate what happened. There we go. Okay. Slow it down just a little bit. There we go. So we're at 10 seconds before launch. The arms of the gantry pull back. The bottom stage is about to ignite. The bottom stage actually ignited for about a second or two, a couple seconds before this guy actually took off. So the S1C is the bottom stage. And there we go. We have liftoff. So as this is animating, I'm just going to walk through the process over here on the right-hand side of how I modeled this. For the launch segment, I went with a standard launch segment inside of Astrogator. It's a pretty generic launch segment where you say this is my start location, this is my end result and velocity. In order to get in all to the multi-staging details, it kind of passes into another domain of ITAR, and so I didn't get to that level of detail for the launch segment. But we have all the stages just falling off at the right times and going into the ocean. So I'm going to open up the properties here. So you can see for the launch segment, I targeted the burnout altitude, the latitude, the longitude, the horizontal flight path angle, so how circular the orbit is, the direction, and the final magnitude. These are all the things I tweaked in the launch segment to line up with the actual values given to me from the Apollo 11 mission report. So I'm going to pull up this table over here. There we go. So I tried to match and go through and match pretty much the latitude, the altitude, the space fixed velocity, the flight path angle, and the heading angle. Not the wonderful Cartesian elements that you normally get. I'm going to go and speed up this guy just a little bit. Oh, wants me to close this control panel first. Speed this guy up over here. And at about 2 minutes in, you'll see the second stage fall off. But going back to the table, I tried to match all the values in this mission report to within a fraction of a degree, and I tried to hit all the feet per second. They liked using an interesting mix of units. Back in 1969, they used feet instead of meters, and you can see that first stage fell off right there and it falls into the ocean. And they like using nautical miles. These altitudes are actually nautical miles. So that was a fun process to go and convert all these numbers and just to cross-reference everything. So going back into STK over here, you can see in my targeter, which is what I use to just make sure I hit up, land in the right locations. I hit all those values from the mission report. Okay. So the second stage is now burning. It burns for about 6 minutes or so, about 6 minutes and 30 seconds, and then it too will fall off. And as soon as these stages fall off, there's only a second or two before the next stage ignites. So this whole sequence is done with the launch segment. So we're going to allow our animation over here to catch up. Just going to speed up just a little. So at this point, we're gaining altitude. The end result of all this is a 200-kilometer orbit, so it's pretty low. And there we see the second stage flew off with the ring that connects the two the upper stage and the first two stages of the Saturn rocket. So there's the first stage, the S1C, that's already flown off. The second stage just flew off. And the S4B, this is actually the third stage of the rocket, but it's called the S4B because originally it was supposed to be, I believe, 4 stages. So we're just going to jump to the time. So this Saturn 4, the upper stage right here, just finished burning. So they are now in a 200-kilometer orbit, orbiting the Earth. So we're going to jump, and they do this for another 90 minutes, and we're going to jump to the Translunar Injection. So this is where about an orbit later, after being in this 200-kilometer orbit, they're going to light the main engine again, the S4B, and we're going to go to the moon. All right, just going to jump to a different camera path right over here. Okay. So we just finished the launch. We orbited the Earth for 90 minutes. The Saturn upper stage, the 4B, is now burning. In order to do that, I used another target sequence. This time, for almost all the burns, I didn't use impulsive burns. I used finite burns to do all the burns here. This one is a constant pointing direction with a constant thrust. And in order to build these engines, I had to go and get all the mass of all the spacecraft, make sure all that lined up. Sometimes I wasn't able to get the correct ISP or maybe the exact thrust, and sometimes I get conflicting data sources. So you can see from the values that I put in, or what I thought the maximum nominal thrust might be, we found a solution of 92% of my estimated thrust, which it means my initial guess was pretty close. And almost all my target sequences, as we go a little bit further along, are going to be 95, 99% of my estimated initial value to target these guys. And what I targeted at the end of this was the horizontal flight path angle, so how circular my orbit is. We're no longer circular. We're going towards the moon now. The velocity after the end of the burn, and the burn direction. There's also, in a lot of my target sequences, you'll see altitudes, latitudes, and longitudes. And these are just verifying that I'm pretty close in location to where I'm supposed to be. Okay, so after the crew, they are now on their way on a free return to the moon. TLI has commenced. We're going to jump to the command service module, transposition and docking. So only about 30 minutes or so after they perform this TLI, the crew, I'm going to slow that down, actually replay that guy. That was a little quick. So on the way to the moon, the command module, which is which is attached to the upper stage of the Saturn 4B, actually comes out, separates from the upper stage. The payload bearings fly off, goes out about 100 meters away or so, and then it turns around, comes back, and reattaches with the command service, with the Lunar Module, which is inside the upper stage of the Saturn 4B. So to go through the parts of the spacecraft, we have the service module and command module, which you can see in the screen right now. And it's going to, in a moment, do a 180-degree flip and then come back around. So it goes out, they stop, they turn around, come back, and they're going to get the Lunar Module. The Lunar Module is what it actually lands on the moon, and they're going to go and reattach and grab that guy. See if we can get a slightly different view. There we go. It goes back in, and it pulls out the Lunar Module from the upper stage of the Saturn rocket. So we're going to speed up to go back and see this guy. So this whole process takes a couple minutes. They're not in too big of a rush. So they come back in, redock with the lunar module, and then the upper stage is going, and the service module, now they're going to be attached. It's going to pull the lunar module out. So we're going to jump to that. So you can see a little bit later, we're going to pull out the lunar module from the upper stage of the Saturn IV rocket. These guys are going to separate. And this is on the way to the moon. So right now, the upper stage of the Saturn rocket and the lunar module and the service module with all the astronauts in it are on the way to the moon right now. So if we jump to the separation event, let's see, there is the lunar module and service module. They perform a maneuver to separate so that they don't hit each other, and then they are on the way. Okay, so the next stage, they do a mid-course correction, but on the way there, they do something called a barbecue roll or a thermal balancing roll. So we're going to jump to that. And this is in relation to what the crew's actually doing in terms of attitude. They end up pointing the nose of the spacecraft of the service module north, and it's not the north that we traditionally think of. It is the north ecliptic pole, which is the orbital motion of the sun. And the reason they do that is so they can spin their spacecraft so at about 3 degrees per hour or 3 revs per hour, and then they can evenly heat it from the sun. So I'm going to speed this up just a little. So I would say, I don't know what fraction of the time, but most of the time during their translunar journey, the Apollo capsules are rotating at this 3 degrees, 3 revolutions per hour to have this thermal balancing, so their spacecraft gets heated. So one side doesn't get too hot from the sun, and the other side, not exposed, gets too cold. So they're rotating this entire time. And they stop every now and then to transmit back down to Earth, but this is what they're doing most of the time.
The time in the lower left-hand corner, is that simulation or mission time, or?
So the time in the lower left-hand corner is mission elapsed time. So that would be the time from July 16th at 1332 minutes of UTCG or prime meridian time. So right now the crew is 11 hours into the mission. 11 hours from liftoff, now they're 12. And then they're in this thermal roll. And they're going to do that pretty much all the way to the moon. So the crew is in that thermal roll pretty much all the way up until the lunar approach.
So now we're at like day 3.
So yeah, for day 3. So we jumped 2.5 days just like that. Magic over here. So they spend 3 days coming into the or during the transit. It's 3 days long. All right. So back to how I built all this. We had the transposition, redocking. These are all just propagate segments. None of that really affects the orbital motion here. I targeted a mid-course correction, and it performed a small burn that only lasted a couple seconds or so. So there's a mid-course correction that happened that put these guys on the right entry path. Oops. They go around. That put them so that they land or approach the moon in their desired location. So what you just saw right over here was the crew enters behind the moon. So right now they can't see the Earth, and they have to perform something called TLI or Translunar Lunar Orbit Insertion. Sorry, got my acronyms mixed up there. They're performing this maneuver called LOI, Lunar Orbit Insertion. So they're behind the moon. They have to burn. This is like a huge burn. This is almost a kilometer per second burn. It's like probably like 600, 700 meters per second to slow this guy down. And what they're doing now is they're slowing down their speed to get captured by the lunar gravity. If they didn't slow down, what would happen is they would come back and return to Earth if they didn't burn at all. That's what the free return trajectory is, and I can show that. I'll probably show that a little bit later. But if this burn didn't go correctly, if this burn messed up, you burned the wrong magnitude, and let's say the engine were to fail, they would either be stuck in a lunar orbit or they would sling off into some Earth-lunar interplanetary space and stay in one of those orbits. So there's a real critical moment. They can't talk to the ground right now, but luckily everything, as we know, went fine.
Austin, can you
Yeah.
talk for a second about the model that you're using in terms of gravity fields and different segments and propagators and such?
Sure. So target sequence, we target the mid-course correction. For this lunar orbit insertion, I'm going to open up the properties of this maneuver. By default, during all these finite burns, I'm using something called the Moon HPOP, which is the High Precision Orbit Propagator. So these are not just point masses. These are propagators that real missions would use, like pretty high level of fidelity. This is not, what you learn in your second or third year in undergrad. This is, optimized libraries that you might touch on in like grad school. So if I open up the propagator, just to show you real quick, we are accounting for, in this case, a gravity field, so a 48 by 48 gravity field. Since the Earth isn't a perfect sphere, you can kind of get this weird shape and sort of account for the gravitational hills and bumps. And this is 48 by 48 degrees. And without going into that too much, we're accounting for all the spherical harmonics out to a pretty high level. There's something called solar radiation pressure, which is the sun, when it can see you, actually pushes on your spacecraft from all the photons hitting it and being absorbed, or hitting it and reflecting. And we're also counting for third body effects, such as the sun and Earth. Of course, you could go in further detail, but this is what I thought like a pretty high, medium high fidelity solution for modeling these orbits.
Did you change propagators when you're closer to the Earth and closer to the Moon?
So great question, Cody. I actually, yes, I did. Somewhere around the mid-course correction, I'm using the Earth HPOP, and then later I use a Moon HPOP. And the main difference there is originally the Earth has all those higher level gravitational terms being accounted for, and then at some point I switched so that the Moon is now the primary central body and has all those gravitational forces accounted for, because at a large distance, all those higher order effects don't really matter as much. Thanks for the question, Cody. All right. So we are now in orbit around the Moon. The next thing they do is something called lunar orbit circularization. So here's a little bit different view. The original orbit they entered in was a 170 nautical mile by 60 or so nautical mile. I'm not going to try to translate that to kilometers off the fly for you guys listening. But the next thing they do is once a couple hours later, they burn again, and now they're a little bit more circular orbit. So it's slightly elliptical, and then they burn again to now have a more circular orbit. So there's the Earth in the background. So they're going around the Moon this way. All right. So now for some might say the main event, where the crew actually goes down. So let's go ahead and jump to that. Here we go. Okay. So down here on the bottom, you can actually see the lunar landing site. There's a plan and the actual landing site. The service module and the lunar module, they separate. They perform a small maneuver to separate. And if I play this, right over here, I have something called a data display, which you can turn on in STK, and you can see information as you animate through time. So right now you can see our altitude up here in feet. we have our altitude rate, our lat long location, our velocity with respect to a non-rotating moon, and the velocity with respect to the landing site, which are going to be pretty close because the moon does rotate slightly, so it stays tidally locked to Earth. But these numbers are going to be pretty close. And those are going to match pretty well up until the final landing. Okay, so the service module and lunar module have now separated. You can see the lunar terrain here. They separate sort of near the landing site, and then they're going to go down. They're going to soon perform a maneuver called the descent orbit insertion, the DOI, which is a little bit later. And what that does is it brings their periapsis, or their closest point to the moon, down. And it lowers that. This is a 30-second burn. They burn for 30 seconds to lower their periapsis up until they're just a couple miles above the lunar surface. So we're going to go ahead and jump to the final descent over here. So this is where modeling, I really had to, I tried a couple different approaches and added even another layer of fidelity here to model this appropriately. So what we've looked at so far is the service module. That stays in orbit, so Mike Collins is all alone in orbit right now, whereas Neil Armstrong and Buzz Aldrin are in the ascent module here on their way down, or they're in the lunar module on the way down to the landing. So we're going to switch to a different satellite now. So if I open up the properties of my descent module, I'm just going to animate this. The burn burns for about 12 minutes. This whole process takes about 12 minutes to actually get there. You can see up in the top the thrust level. So they're at about 93% thrust. I'll slow this down just a little bit. You can see the altitude dropping, their altitude rate, their lat long, and their velocity. So that the 93% takes 5 or 6 minutes or so. And to show you how I actually modeled this, let's see what page this is on. Okay, so the thrust profile is right here. So this is the actual thrust profile from the mission, the data that we have available to us. If we look at this, so over on the left-hand side, you can there is an axis for percent thrust, and it starts off around here low, about 13% or so, and it jumps up. This dashed line is that percent thrust of like max full throttle. The Apollo 11 spacecraft couldn't fully throttle its engine, so it had to go kind of all the way on, and then it could operate at about less than 60%. It was throttleable under about 60% threshold, but it was 93% for most of that burn there. So you can see we are at 35 minutes, which would put us somewhere around here during the burn, and then they're going to cut down to about 56% and drop slowly, and they keep about 25% of the thrust all the way until they land. So in order to model this in STK, I originally pulled this data into MATLAB by using a handy tool I learned back from undergrad when I was looking at this data for the EVAs. I used something called a plot digitizer, which pretty much allowed me to click out the points on this plot right here and convert this into a digital format. And then after that, I was able to pull that data into MATLAB, and Astrogator and STK are really great about this. So what they allow you to do is integrate with other sort of tools. So in this case, I integrated with MATLAB, and I have a engine model plugin. And so what this does is returns the thrust, the ISP, the mass flow rate of my engine, and then all the values that are used actually come from the Apollo 11 mission report. So you can see at time 0, I'm about 14% thrust, and then I have 93% thrust for a while, and I slowly drop down. So all this is actually physically being used, and all these calculations are being performed inside of STK. And so this is what I use for the vast majority of the descent, is I linearly interpolate between these data points and use the actual thrust profiles from the mission. So I'm going to pull up another graph. So this is a MATLAB figure that I made. You can see that thrust profile, which is this blue line. So this is the data inside MATLAB, which matches pretty closely. Different scales here, but pretty closely to the Apollo 11 mission report. So that's this light blue line. And then the other data on this graph, these blue dots are the pitch angle. So how much the spacecraft is pitched. So how much it is turned with respect to kind of the horizontal of the moon surface. And you can see it starts off 90 degrees would be completely horizontal. So they're a little bit above horizontal when they first start burning, and then they slowly pitch over. And as you can see right over here, this guy is not 90 degrees anymore. He's turned over some. Going back to our figure. These are all the data they pitch over, and it's not really like a constant rate. It goes back and forth a little bit up until the landing. You can see, especially down here, it wobbles back and forth a good bit. When Neil actually took over, instead of autopilot, Neil commanded the spacecraft all the way down to the lunar surface. So in order to model this in Astrogator, what I used was something called that was introduced, I believe, in a STK 11.4, and that was something called a time variable finite maneuver. So if I look at these, the lunar orb descent was a standard constant thrust, constant direction, get me in the right direction, right location. But for the rest of these, this 13%, 93%, 56%, I use something called a time-varying thrust. And what that does is allow me to specify an initial pitch angle, how much I change over time, a linear term, as well as a second-order term. And I could go out higher here, but I didn't do that. Instead, I used a second-order fit to kind of fit the data between the key mission segments. I'm going to pause right here, interrupt myself. So right before landing, at probably 4 or 5 minutes before they actually landed, they get this lovely warning. They get a warning like during the final moments of their approach. So mission control had to talk to the crew during this time to decide if they wanted to abort or if they wanted to keep on coming down. So this warning message actually flashes up, I believe, at least 4 times during their actual descent. Okay, I'm gonna go back right over here. So from those polynomial fits, I was able to do a series of time varying thrust arcs. So from this figure, these black lines are the thrust arcs that I fit and gave as initial guess into STK. These black lines right here, and this other figure is the actual values that were used. So if we look at this dashed blue line, these are 2 different reference frames, but if we look at this dashed blue line, we're trying to follow this kind of red or this black line right here. This dashed blue line is what STK calculated to hit for the pitch angle in order to actually land the spacecraft. In order to hit the altitude, the descent rate, and the velocity at key points throughout the descent, ST calculated a slightly different pitch angle than with the actual mission report. And the reason for that is I didn't perhaps come in exactly as the Apollo astronauts did. Sometimes there's coordinate frame issues. All these coordinate frames and all the data they were giving me was from the 1960s. They're using 1960 coordinate frames. So doing all those unit conversions and get everything in the right coordinate frame Sometimes everything doesn't line up exactly, but this is still a really close fit. And when I go and look at all my thrust profiles and things like that, they match within a percent or two in all the cases. Okay, so the final moments of descent, we're going to speed up just a little bit. The last phase, we're going to actually just go ahead and jump to 500 feet. Here we go. So they're coming in, and right now, at about 500 feet or so, Neil actually takes over. So a few seconds before this, he's realized that there was a large boulder or crater in the way, and that he did not want to land in that large crater. So Neil took over from the automated control about 500 feet before the actual landing. You can see the green spots where they actually landed. In order to model that, the approach I just talked about with the time variable thrust and using an engine model plugin with a kind of using the actual data, it worked really well up until these last couple feet, 500 feet or so. And once Neil took over and kind of did his own thing, I couldn't follow it precisely. So instead, I followed the approach by one of Astrogator's original developers. If I go ahead and pull this up, and they use this concept of a kinematic lander, pretty similar to what you would learn in your high school physics class. It says, oh, I'm moving at this rate, and I want to be at this location and move at this rate, and some amount of time later, calculate, how much thrust would I need to, on average, get me to that spot. So I'm using a kinematic lander for the last couple of feet or so, because I couldn't add in all that fidelity in any reasonable amount of time frame without just forcing the trajectory to go where I wanted to. Instead, I changed the thrust so that I target the landing and that I land at the desired speed and in the desired amount of time that I wanted. So right now, Neil's taken over in these last couple 100 feet or so. And you can see at this point, the spacecraft is almost entirely pitched up. So it's almost directly straight up. It is not the same direction as the velocity with respect to the moon. And then we come in for the final few moments before the landing, as you can see here. So the pitch angle you see is the actual pitch angle from the mission report. So this is the actual attitude they flew. There was a little bit of a roll motion here, as well as a little bit of side-to-side motion. I didn't capture that all here visually, but the pitch angle is really what is needed to land in the right location. It affects most of your thrust and landing spots. Okay, so we've landed. And that happened 4 hours into the mission, 4 days, 6 hours, and 45 minutes into the mission, and about 40 seconds or so. And both Neil and Buzz are now on the lunar surface.
Does that represent the actual topography of the moon?
So great question, Craig. You may notice that some of the imagery is slightly different colored here. Basically, what I have in STK right now is all the data from the LRO, which is the Lunar Reconnaissance Orbiter. That's actually in orbit around the moon right now. And its job is to map out the moon and give us a much higher resolution terrain for the entire moon. So you can see all the, in the background, you can see all these mountains. Those are real. That's coming from a real satellite in orbit right now. This is where they actually landed within as accurately as we could do. So this is where they actually landed. And what you can see right here is an image overlaid on top of the moon because we don't have as high resolution of imagery for this one particular spot. So we without this image. So we have this image on top. And then a different image that has a slightly higher resolution than my global moon. So this is all real. This is all accurate. This is a composite of a couple different images. That's why you see that discoloration there. Good question. And the original planned landing site was actually back over here. In this sort of ellipsoid was their, I guess, OK zone, or their probability of ellipse for when they landed. So they're approaching the edge over here. All right. So the next important thing was one small step. So one small step for man, one giant leap for mankind. That happened about 6 hours or so after Neil and Buzz were on the surface. And this is just the generic. This is not the actual path they traveled. They went out, they planted the flag along their time here. They also traversed around, set up some lunar experiments. And there's only one extravehicular activity. They had a call with Richard Nixon at the time while they're on the moon, and then they re-entered. So the Lunar Module pilot, fun fact, actually doesn't really pilot the Lunar Module. That'd be the commander, which would be Neil. So Buzz would be the Lunar Module pilot, although he didn't actually have like the joystick or the steering wheel, so to speak. It was actually Buzz. And then for EVAs, it is traditional for the commander to get out first, and then a few minutes later followed by Buzz, the Lunar Module pilot, and the Lunar Module pilot gets back in, and the commander follows. At least that has what was done for the Apollo missions, and what happened here. Okay, so right before liftoff, the one other important event that happened was Russia. So this happened back in the space race. Russia actually crash landed a lunar probe into the moon. This is an hour before the crew is set to come back off the lunar surface, and so they landed not particularly close, but the probe actually landed just an hour before the crew took back off. So they're on the moon right now, and Russia crash landed a probe. So just a little bit of nature to the space race.
Do you think they were aiming for them?
Perhaps. I mean, they get kind of close. It's kind of hard to aim. Probably not, but yeah, Luna 15 crash landed, trying to steal some thunder. I don't think they were going for a crash land, but that's what happened. Okay, so the next stage is liftoff. We want to make sure our astronauts get back home. So we have the ascent stage that lifts off the lunar module. And to model this, I'm going to pause it real quick and open up the the lunar ascent stage. I also use a launch sequence, which is probably more accurate on the moon or more applicable on the moon, because this is following a cubic spline or a quadratic motion here. And because there's no atmosphere, or no large atmosphere on the moon, this is pretty close to the trajectory that the ascent profile would have taken. So after lunar orbit insertion, they took off from the moon. Both Neil and Buzz are in the lunar module right here. They start something called a co-elliptic sequence maneuver. And basically what this is they have to launch at a precise time to make sure that they are able to catch back up to the service module, which is ahead of them in orbit. So lower orbits move faster than higher orbits. So they have to launch at a precise time. So by the time they drift up from this lower orbit to the higher orbit, that the orbital phasing matches up, and they can actually rendezvous with the service module, which is in orbit with Mike Collins. So this is a multi-staged event. The first part is the co-elliptic sequence. Then there is something called the constant differential height maneuver, which kind of puts them at a constant height with respect to each other. These are going to be, it's going to put from an ellipse to a more of a circle, so two circles. one smaller circle, one bigger circle, and then there is this last phase called the terminal braking. So if we jump to that. So the lunar module is catching up to the service module at this point. You may actually notice there's something back around the S4B. That's the upper stage of the Saturn rocket. And in a few moments, I'll show you what happened to that guy. But the lunar module is catching up to the service module. They're braking right now so that they line up with their final velocity. And then these, in order to show you how to target how I did this, I used another target sequence, but instead of targeting lat-long locations, in order to get the final orbital rendezvous, I used something, a relative motion. So this is done when you're doing relative motion between satellites. This was a big deal back in '69. I targeted an in-track rate, which is how far long my orbit is. Cross-track would be side to side, and the radial would be up and down. I wanted all those rates to be 0, so I can rendezvous right in front of the lunar module. So it looks like we're running a little low on time, so I'll speed up just a little bit. So you can see the lunar ascent module come up and slow down right in front of the service module. And then over the next few minutes or so, the lunar module, the ascent module will slowly come back in and rendezvous with the service module that's in orbit right now. So that is the lunar docking. And you can see that guy come in. And one of those iconic shots that's on the front of my Bate-Mueller white textbook, I believe came around about now, where you have the service module and it takes an image of the ascent module, the upper stage, and the moons or in the Earth in the background. So that's one of those classic shots that happened right about now. This is 5 days, 7 hours into the timeline. So you can see the two come in and dock. There we go. So after this, after docking, as amazing as Eagle was, the lunar descent module, they do get rid of the upper stage and they leave that in a lunar orbit because it doesn't make too much sense to carry this big hunk of mass back around with them. It would have been great for historical purposes, but instead, from a fuel and energy perspective, it makes more sense to leave this upper stage back in a lunar orbit. So they jettison the upper stage of the lunar ascent module, and now all the crew is in the service module. So they leave the ascent module behind, and then they move on to their journey back home. So their trans-Earth injection. Okay, so again, they are on the dark side of the moon. Or they're actually not on the dark side, they're on the far side of the moon. Those don't necessarily line up. They're on the far side of the moon. They can't speak to Earth, but then they do one of the last couple critical burns as their trans-Earth injection. So they burn for about 5 minutes. I think it's about 3 minutes or so. And now what they're doing is they're increasing their orbital speed. As you can see here, the red segment is when the service module is actually burning. They're increasing their orbital speed to put them back on a return path to the Earth. So now they're coming back home. Okay, and on the way they do another thermal roll. We're going to skip over that for time's sake. But they do another thermal roll, and we're just going to jump right back to reentry. So they do one mid-course correction on the way back to enter the Earth's atmosphere appropriately. So right before reentry, the command and service module, now that these guys have been mated the entire time, they're going to separate in the last few minutes here. The command module breaks away from the service module. The service module was used for propulsion as well as storage throughout the mission. Now all the crew are in this in the command module with the heat shield as they re-enter and they come back in. So right now they're going to be entering the sort of upper atmosphere, and then this would the heat shield would start getting really quite hot, as well as and so that provides a tremendous amount of heat and temperature, as well as actually a lifting force. So if I pull up sort of how I modeled this, I was going off of a couple different sources here. The drogue chutes come out at 24,000 feet. After they've gone through the bulk of the atmosphere and the heat shield, it's gotten real hot. They actually lost communications with ground control a little bit longer than expected. So mission control, if you saw the Apollo 11 movie, was quite worried for a few moments there while they're reestablishing communications. But after that, the drogue chutes deployed, the small parachutes to slow them down a little bit and kind of make sure their velocity is in the right direction. Then the main parachutes deploy and they come down for a safe landing. So I'm just going to jump to the final splashdown over here. And they splashed down when they actually landed just to the west of Hawaii right before dawn at 8 days, 3 hours into the mission. So there is our final splashdown. Then we have a helicopter and a ship coming out to recover our crew. Thank you, Craig. All right, so our astronauts made it home safely, as we well know. Just a few last things I wanted to point out. I know we're running a little short, and then I'll go to questions. So a few things I just wanted to point out. Some interesting things I found was during the recreation of this mission. Sometimes the data sources were a bit conflicting. So I just wanted to point out a few thorns in my side that I thought were pretty interesting. Okay, so on the Apollo 11 mission table in here, one thing that was giving me trouble for the longest time was this terminal phase finalized, which is right when the before the ascent module and the service module redock, and I see 7.6 nautical miles. This is already after they left the moon surface, and they're already 40 nautical miles up. This doesn't really make sense to me. I checked other sources. There's a source called Apollo 11 by the numbers, and they also have it at 7.6. But I really think what happened here, all these original documents are typewritten, was that supposed to say 57.6 nautical miles. So if you ever want to go and rebuild this yourself, be warned. It's incredible that they did this way back in the day. But if you're ever going to rebuild this yourself, be a little hesitant if you get some funny values in here. And then one other one that happened that I ran across was the actual landing location. So in the landing location from the original documents, they said they landed at 13 degrees south, and they actually landed at 13 degrees north. Later on in the document, they do use 13 degrees north, so it's a little bit of a mismatch. So those are a couple typos that happened found along the way that were pretty interesting. One other thing that is, I would say, even more slightly interesting is this iconic figure 8 pattern of the Earth to Moon kind of trajectory. And if we want to look at that inside STK with the actual physics here, is it looks slightly different. Let me just go ahead and turn on the entire orbit here. Maybe I have to go back just a little bit in time. But there we go. Okay. So what you see here is a little bit different than that iconic nice figure 8 pattern where it gets pretty small towards the moon. They go into lunar orbit, then they go to the circular orbit. What actually happens is a little more goldfishy, is how I'd like to describe it. This isn't the Earth-Moon rotating frame.
I believe that's the correct technical term.
Goldfishy, yes. That's what I thought. But it's pretty interesting that the actual trajectory, all you learn, what you learn, in physics class, or in orbital mechanics, or when you first learn about Apollo, is this nice figure 8 free return trajectory. What actually happens in the real world is the moon and the Earth are actually moving a little bit with respect to each other. So you go out, and what happened is they actually went out a little bit further. The moon, while they're orbiting, gets a little bit closer to the Earth because the Earth and moon aren't in perfect circles with respect to each other. And then they come back on a slightly different route on the way back. And one other last thing that was pretty cool, which a lot of people either don't know about or forget, was the upper stage of the Saturn rocket. So if we jump to that real quick. So that's all the trajectory to the previous orbit there. But you can see when they're first coming into the moon for the first time, and the crew go into this orbit around the moon, the upper stage actually comes in a couple hours later and flies by them and gets slung out into this heliocentric orbit. So the upper stage of the Saturn rocket is still out there today. So it's in a heliocentric orbit. It did a flyby, whereas the crew went on the other side of the moon and slowed themselves down. So those are just a few things I learned throughout rebuilding this. Thank you, everyone, for coming. We're going to take a few questions here. And, yeah, thank you, everyone, for coming once again.
Okay, thanks, Austin. Okay, thanks, Austin. We do have a few questions, and we have actually a lot of questions. So I'm going to try to get through as many of these as I can. And then if we don't get to your question, I'll have Austin follow up with you. And then you can always email questions in at info@agi.com, and we can answer them. One question is, how were the astronauts simulated on the moon? Are they just ground vehicles with astronaut models?
So, yes, in this case, STK is analysis software for satellites and aircraft and ground vehicles. And in this case, the astronauts were just ground vehicles that were walking. I originally clicked out all the path after watching a couple hours of footage from all these and tried to recreate it from all these camera angles, but I didn't want to necessarily be historically inaccurate, and it was taking a while. So they're just a ground vehicle to go and plant the flag and come back home or to their ship.
Okay, thank you. At what actual point do you change from the Earth as central body to the moon as central body?
Okay, I do that. I think right after the mid-course corrections, sometime around there. So if I open up the service module, which is doing most of the propulsion, let me open up the properties. I do that. I think right after the either the mid-course correction or right before lunar orbit insertion. You can also have multiple gravity fields, so you don't actually have to switch propagators, but in terms of computational efficiency, it makes it a little bit easier. And then once you're really far away from the Earth and Moon, modeling of its point mass is pretty accurate enough.
How did you get the warning message into the data display?
Okay, that's a great question for you STK users out there. If you go, it's actually not in this panel. It's on my moon panel.
Isn't everyone STK users?
They should be.
Yes. If you aren't an STK user after seeing this presentation, you should be now to see all the cool things that you can do, especially with all these 2024 missions that are coming up. I want to see what you guys can do next time. But for the annotations, if you open up the properties of your 3D graphics window, there's a tab for annotations, and you can add text boxes that appear, and then you can set the display times right here. So these are the times the alarms pop up. They popped up 4 times during descent. So that's how I add it.
Shipping up or bundling up the scenario and shipping that out to anyone that wants it?
So that's a great question. So what we're actually so we do already have webinars in the next couple of weeks. So we're actually going to build this scenario from scratch. We're not going to bring in all the models and imagery and some of the terrain, but we will build the trajectory almost at the exact same level of fidelity that I did from start to finish. That'll take 3 sessions. I think first one's coming up around June 4th or so,
yes.
And then every week after that. So we will rebuild it, and you don't need MATLAB to do it. I took all my MATLAB scripts and put them in VB script, which is what on all Windows computers, so you should be good to go there. You're going to need 11.6 to follow along. We're still working on a few of the details for some of the articulations and like some of the thrust firings, some of the attitude segments. Just double checking all of that is 100% right on the sort of the latter half of the mission. So once we get all that, we're actually going to put it in something called the Event Viewer, which is Cesium, which is another thing that AGI does. And that would be a web URL you could kind of log into and see it. So you wouldn't need actually to have STK installed. You could go to that Cesium viewer, and we are going to have events you could jump around the mission, and it'd be a great visualization tool. And we also may release the scenario in the future. That's to be decided.
Okay, thank you. Lunar Surface module that is orbiting the moon forever.
Mm-hmm. The Ascent module.
So that's just going to constantly orbit the moon.
So I think at some point, I don't know how many years later, it did come back down and crash into the moon. I don't know.
R.I.P.
Yeah, R.I.P. But that took years, I believe, to come back down. Cody, do you happen to know?
Off the top of my head, no.
Okay, but I think a couple years later, it deorbited it deorbited. Gravity, yes.
It's just the higher order gravity terms that are going to pull you down eventually.
Yeah. If you model as a point mass, it wouldn't, but since we're doing higher order propagation here, it would have if I propagate it out into the future long enough.
Okay, we're gonna stop because there are just a lot of questions here that I don't think we have time for. I think they're gonna bring us down too far into the weeds. So I'm gonna have Austin respond to those, or Cody respond to those offline. But if you have any questions when you go home tonight and you're thinking about this webinar, which I'm sure you will be, you can email us at info@agi.com. You can also look for future webinars at agi.com/blogs. We did record this on video, so you'll be able to catch that on our YouTube channel at youtube.com/analyticalgraphics. And you hit the like and subscribe button there. Actually, it's the subscribe button on YouTube. Hit the little bell icon and you can get notified of our latest postings. Thank you, Austin. Thank you, Cody. I think what we proved today is that this was not created in a Hollywood basement with Stanley Kubrick directing it, and that is incredible engineering prowess that we have. So again, thanks, guys, and hope to see you at the virtual training on June 4th. And again, thanks again.